Chemical systems are always trying to get to equilibrium. And once they reach equilibrium, they really want to stay there. But sometimes things happen which cause a disturbance. And when this happens, we have Le Chatelier's principle to guide us in figuring out how the system will respond to that. And the basic rule is the system is going to try and minimize that disturbance. The system is going to try and get back to equilibrium. So it's going to do whatever it can to counteract whatever disturbance it just encountered. So there are three basic types of disturbances we can think of. Adding or removing a reactant or product will disturb equilibrium. Changing the volume or pressure can disturb equilibrium, and changing the temperature can disturb equilibrium. So we can use Le Chatelier's principle to guide us in figuring out how my reaction will respond if I make one of these three changes. The rules, it turns out, are really simple. Just think about the disturbance and then try and do the opposite. So for instance, let's say you add a reactant or product to your reaction that's at equilibrium. Your reaction is going to try and use up that new molecule. So let's say you have a really simple reaction, A plus B goes to C, just something like that. That's a plus sign there. And I add some of A. Well, that's going to disturb equilibrium because that's going to mess up that equilibrium ratio of products to reactants. So my system is going to try and get rid of that A by shifting to the other side. It's going to try and make more products. If I had added C, on the other hand, it would do the opposite. Now I've messed up that ratio by adding too much product, so it would try and shift in the opposite direction and shift back and make more reactants. Really, really similar. If I remove something, now it's going to try and fill that gap. So if I have this A plus B goes to C, let's say I remove some of my A, well, now I kind of have a hole that I need to fill in, so the reaction's going to shift in that direction to try and make more of that A. So it's going to shift to the same side as the one I removed something from. Now this only applies to molecules that actually appear in the equilibrium expression. So for solids and liquids, it's not going to have any effect. So we have to always keep in mind that solids and liquids, they're not included in the equilibrium expression, so they're not going to affect my equilibrium. Next one we can talk about are pressure and volume changes. My basic rule here is just think about how much stuff you have and if you have enough room to fit it all. So for instance, let's say you took a reaction and you decrease the volume or increase the pressure. When you do that, that's really limiting the amount of space you have. So your reaction is going to try and shift to the side that has less stuff, or the side that has fewer moles of gas. So if I have A breaks into 2B, for instance, and these are all gas molecules, if I increase the pressure or decrease the volume, it wants to shift to the side that has less stuff, so it's going to shift to this side. We only have 1 mole of A on this side, whereas if we have 2 moles of B on this side. On the other hand, if you decrease the pressure or give it more space, it's going to shift to the side with more stuff because it has more space and it wants to fill that space. Nature abhors empty spaces. We always like to fill it. So if we increase the volume, it's going to shift to the side with more moles of the gas. Now, this only applies if you have gaseous molecules. So you ignore any of the solids and liquids. Just look at the gas molecules. Ignore anything else. The last thing we can do to change the pressure or volume is to add an unrelated gas. That really doesn't do anything. It's going to affect both sides equally. So if I add an unrelated gas, so a gas that does not appear in my chemical reaction, I can basically just ignore that. Last thing we have are temperature changes. And we see examples of this all the time with phase changes. So we think about ice melting. So that's only going to happen if we increase the temperature of the ice. That's the only time it's going to melt. Whereas if we decrease the temperature of water, it will eventually freeze. So for that equilibrium reaction, H2O liquid to H2O solid, that's an S there, we can see that we can shift this equilibrium to one direction or the other by changing the temperature. So if I make it colder, it's going to shift towards the solid. If I make it warmer, it's going to shift towards the liquid. So temperature often affects chemical equilibria. Now the key thing here is the first thing we need to do is figure out if we have an endothermic or exothermic reaction. And this will be given to you in the problem because you can't figure that out just by looking at the chemical equation. The basic idea is if you have an endo or exothermic reaction, figure out which side the heat goes on. So for an endo reaction, you're putting heat in. So let's say I had this simple reaction again, A plus B goes to C, and I told you this was an endothermic reaction. So for endothermic reactions, that means you're putting heat in. So what I do is I just draw that over on my reactant side. So endothermic, heat goes on the reactant side, and then I'm basically going to use the same rules I used up here. If I add something, it's going to shift to the other side. If I remove something, it'll shift to the same side. So if I increase my temperature, that's adding heat, so it's going to shift to the other side. If I decrease the temperature, it's removing heat, so it would shift to the side with the heat. So same exact rules I used up here. Now, of course, if you have an exothermic reaction, so let's see, we had this and I told you it was an exothermic reaction, then you would put the heat on the product side because exothermic reactions release heat. After that, same rules, add something, shift to the other side, remove something, shifts to the same side. I also just like to note, when you change the temperature, it's actually fundamentally changing the value of your equilibrium constant. And that's why throughout problems with equilibrium constants, it always gives you the temperature, because that only applies at that particular temperature. So these problems are pretty straightforward. They usually give us a chemical equation like this, and they often give us a context clue about endo or exothermic. And they simply asked us to predict how the reaction will shift to each of the following disturbances. So let's go through this and use our rules above. So first one, carbon is removed from the reaction mixture. So I'm going to look at where carbon is, and the first thing I'm going to notice that carbon is a solid. Solids and liquids don't do anything. So this is going to be no change. If I add or subtract solids, liquids, doesn't matter. Next, O2 is removed from the reaction mixture. So I have O2, he's a gas, so I do need to worry about him. And if I remove, I shift to the same side. So that means this is going to shift towards the left or towards the reactants. Because I'm removing that oxygen, I need to make more of it. The temperature of the reaction is increased. So I'm going to go back to this context clue, exothermic. Exothermic means I released heat. So I'm going to put heat on the product side, and now I'm just going to remember my rule about adding or subtracting. So since I'm increasing the temperature, I'd be adding heat, so I need to shift to the other side, so this is going to shift left towards the reactants, away from the heat. The pressure is increased, so what I need to do when it talks about pressure or volume is look at the moles of gas, and on the left side, I only have 1 mole of gas, because again, carbon's a solid. And on the right side, I have 1 mole of gas. So keep in mind this is gas. So if I have equal number of moles on both sides, if I change the pressure or volume, it's still not going to do anything. One side isn't better than the other. So if I have equal moles on both sides, it's just not going to shift. Last one, a catalyst is added. This one's a little tricky because we haven't talked about catalysts, and that's because catalysts have no effect on chemical equilibrium. If we remember, all catalysts do is increase the rate or the speed of the reaction, but it does not shift the equilibrium. You end up with the same ratio of products to reactants whether you add that catalyst or not.